Welcome to the course Antennas and Wave Propagation. Before we explore the course structure, syllabus, key concepts, antenna types, and wave propagation mechanisms that form the foundation of wireless communication systems, let's discover how antennas silently power many of the technologies we use every day. Every time we make a mobile call, connect to Wi-Fi, watch an OTT platform, or use GPS navigation, antennas are working behind the scenes. They act as the bridge between electronic devices and the wireless world. Look around you. Mobile phones, Wi-Fi routers, cell towers, Bluetooth earphones, smart watches, satellite TV, and police walkie-talkies all depend on antennas for communication. Antennas are not limited to communication devices. They are also used in aircraft navigation, weather forecasting, radar systems, satellite communication, space exploration, and defense applications. Designing an antenna is only half the challenge. We must also understand how electromagnetic waves travel through the atmosphere, reflect from objects, and reach their destination. In this course, we will learn antenna fundamentals, antenna arrays, modern antenna structures, antenna measurement, and the different modes of wave propagation. Unit 1 introduces antenna fundamentals. We will study antenna parameters, radiation patterns, directivity, gain, field regions, dipole antennas, monopoles, and loop antennas. Unit 2 focuses on antenna arrays and pattern multiplication. Unit 3 covers Yag-Uda arrays, folded dipoles, helical antennas, and horn antennas used at VHF, UHF, and microwave frequencies. Unit 4 discusses microstrip and reflector antennas. We will also learn antenna measurement techniques including gain, directivity, and radiation pattern measurement. Unit 5 deals with ground, space, and skywave propagation, studied along with ionospheric and tropospheric. By the end of this course, you will be able to analyze antennas, evaluate their performance, design antenna arrays, and understand wave propagation. These are the standard textbooks. These textbooks provide theoretical foundations and practical insights into antenna design, analysis, and wave propagation. The electromagnetic spectrum consists of a wide range of frequencies from radio waves to gamma rays. Antenna systems mainly operate within the radio and microwave ranges. Different RF bands are allocated for communication, broadcasting, navigation, radar, and satellite application. Understanding these bands is important for antenna design. Wireless communication, broadcasting, radar, satellite systems, navigation, and IoT devices all rely on antennas and electromagnetic wave propagation. A communication system consists of a transmitter, channel, and receiver. Antennas play a vital role in transmitting and receiving electromagnetic signals. Polarization describes the orientation of the electric field vector. Proper polarization matching improves signal reception and communication efficiency. An electromagnetic wave consists of mutually perpendicular electric and magnetic fields propagating through space. This slide illustrates the propagation characteristics of electromagnetic waves and their field relationships. Understanding wave propagation behavior helps in analyzing antenna radiation and wireless communication links. Electromagnetic waves transport energy without requiring a physical medium, making wireless communication possible. These visualizations strengthen our understanding of field orientation and wave propagation mechanisms. Antennas can be vertically or horizontally polarized depending on the orientation of the electric field. Polarization affects communication performance. A radiation pattern shows how antenna power is distributed in different directions. It is one of the most important antenna characteristics. An isotropic antenna radiates power uniformly in all directions, forming a perfect spherical radiation pattern. This isotropic antenna is an ideal reference used to compare the performance and gain of practical antenna. Omnidirectional antennas radiate in all directions, while directional antennas concentrate energy in specific direction. This figure shows the spherical coordinate system used to describe the radiation pattern of an antenna. The radiation pattern is represented in terms of the coordinates r, theta, and phi. The major lobe indicates the direction of maximum radiation, while the minor lobes represent smaller radiation levels. The beam solid angle represents the angular spread of antenna radiation and is directly related to antenna directivity. Think of cutting a small slice from a pizza or watermelon. The space covered by that slice is similar to the beam solid angle. It represents the region in which an antenna radiates most of its power. Thin linear antennas form the basis for understanding practical dipole and monopole antenna structures. The current distribution along the antenna determines the resulting radiation pattern at field strength. Beam width defines the angular width of the main radiation lobe and indicates the antenna's directional capability. Directivity measures how effectively an antenna concentrates energy in a desired direction compared to an isotropic radiator. Dipole antennas are widely used in broadcasting and communication systems. Folded dipoles offer higher input impedance and are commonly used in Yagi-Uda antennas. Loop antennas are used in radio receivers, navigation systems, RFID applications, and direction finding equipment. Antenna arrays combine multiple elements to increase gain, improve directivity, and enable beam steering in advanced communication systems. Parasitic antennas, such as Yagi-Uda arrays, use reflector and director elements to enhance gain and directional performance. Microstrip antennas are lightweight, compact, and widely used in mobile phones, satellites, GPS receivers, and modern wireless devices. Parabolic reflectors provide very high gain and are extensively used in satellite communication, radar, and deep space communication systems. In satellite communication, the uplink carries signals from the Earth station to the satellite, while the downlink carries signals from the satellite back to Earth. Typically, the uplink frequency is higher than the downlink frequency to ensure reliable communication. The uplink frequency is kept higher than the downlink frequency because the satellite has limited transmit power. A lower downlink frequency experiences less atmospheric attenuation, allowing the weaker satellite signal to reach Earth more reliably. Reflector antennas improve directivity by reflecting electromagnetic waves toward the desired direction. Corner reflector antennas provide moderate gain and directional characteristics, making them useful in communication and radar applications. A modern 5G smartphone contains multiple antennas such as 5G, LTE, Wi-Fi, Bluetooth, GPS, near-field communication, and ultra-wideband antennas, each serving a specific wireless function. Together, these antennas ensure reliable communication, navigation, connectivity, and high-speed data transfer. Ground waves support AM broadcasting and maritime communication. Space waves are used in television, mobile, and satellite communication, while sky waves enable long-distance HF communication. Thank you for watching this course introduction. I wish you a productive and enjoyable journey through antennas and wave propagation. Have a happy learning experience.